Hi everyone, my name is Rustem. I'm a machine learning engineer at Instrumental, and today I want to tell you how to build scalable end-to-end deep learning pipelines in the cloud. First, let's take a look why serverless is beneficial for machine learning projects. So let's take a look at the usual data science process. So we start with business understanding and define our business problem. Then we try to get data. Then we build model based on this data. And then once model is built and trained, we want to deploy it and get the feedback from the user. But actually, this process is very iterative, and we want to get some feedback from the user as early as possible. So the challenge here is that we want to be able to start fast. We need to be flexible in case our architecture or data sources change, and we want to be able to integrate with existing production infrastructure. So let's now take a look at the serverless approach. So here you can see different ways to deploy application. And depending on the way you deploy it, you control different parts of the stack. Here, I will define serverless as everything between like containers as a service and functions as a service, where basically we control everything above the operating system. In this case, it can be defined as on-demand cluster worker service, which can scale with your consumption. There are no upfront costs, pay-as-you-go pricing, and there is no payment for idle time. It has low operational support, it is defined as infrastructure as code, and finally there are built-in service integrations. So why would we use it for machine learning application? Because of low operational support and no upfront costs, it's very easy to start. Because it's defined as infrastructure as code and there are built-in service integrations, it has very flexible infrastructure in case we need to change hardware type or other things. And since it's scalable and there are built-in service integrations, it can be easily integrated with production infrastructure. And it will be able to handle scale. So for machine learning application in production, we really need to define three main steps. It's data preprocessing, training, and inference. With data preprocessing challenges being scale, training challenges being primarily cost of GPU, and with inference, main challenge being cost and scale. So let's take a look at the service options for compute and workflows. And let's start with compute. So here, let's take a look at the container as a service and function as a service options. We can define the serverless cluster, where basically we have on-demand cluster or worker to scale with your consumption, and where we only need to define code and libraries and launching configuration. And depending on the service, it will have different scaling techniques. For example, with AWS Batch, it will have cluster, which will scale based on job queue. With Fargate or SageMaker, we will have one VM per job. And with AWS Lambda, we will have worker per job. If we compare them together, we will see that Batch provides a more managed cluster option, very customizable, and has the cheapest compute. And with AWS Lambda, we have very scalable option with zero idle time and fast init, but also more expensive. If we compare the cost for the same compute, we will see that AWS Lambda can be like several times more expensive than Fargate or Batch. But you need to remember that with Fargate and Batch, the minimal payment is per 1 minute. So if your job takes then 10 seconds, you still pay for the whole minute. If we compare SageMaker and Batch for GPU tasks, we will also see a difference. Keep in mind that with AWS Batch, you will have some idle time for which you will need to pay. Another question to keep in mind here is, do you really need GPU for your task? We do need GPU for training, but for inference, it may be more beneficial to use CPU because it will have more optimized scalability and cost. If we compare different hardware options for running inference, in this case, Inception Web3 image classification model, we will see that even though CPU, both on like Instance and Lambda, are slower, So you can see here it's like 200 milliseconds, 300 milliseconds, compared to 50 or 20 milliseconds with P2x large and P3x large. Cost per 1 million prediction can be actually lower on CPU instances. Another thing to keep in mind here is that if you have less than 1 million predictions per month, using AWS Lambda can be more beneficial because you don't pay for idle time. So if you don't have a lot of predictions per month, it's more useful to use Lambda. So now that we have covered compute, let's take a look at the workflows for machine learning applications. So why would we want to use them in the first place? Let's say we have some application, we run it on GPU, but do we really need GPU for all the steps? We do need it for training, but maybe not for data preprocessing or data gathering. So in this case, we can basically optimize the application to minimize GPU idle time. And in this case, we will have more suitable service for each individual step. But we need some glue to connect these services together. And that's where cloud-native workflow services come in handy. Basically, it's the usual workflow, but every node can be a different FAS or CAS, and you can use the service for monitoring, logging, and tracing. So there are multiple options for this type of services on AWS, starting with managed airflow to AWS Step Functions and SageMaker pipelines. Managed airflow is more customizable, but it's not as scalable. Step functions are more suitable for production applications, and SageMaker pipelines are more suitable for research applications. So now let's take a look at the patterns for machine learning pipelines. With serverless approach, we will use Lambda, Batch, SageMaker, and Fargate for compute, and the step functions to organize workflows, given it's suitable for production and also scalable. So let's start with data processing. So first option is to use SageMaker for the processing, and using other services like Lambda for scalable processing, which can be parallelized. Another option is to use AWS Batch or Fargate where we try to run more heavy processing tasks on containers as a service and more parallel processing tasks on Lambda. One thing to keep in mind here is that with SageMaker, reading and uploading data comes for free. With Batch or Fargate, you will need to implement readers and writers on your own. Feel free to check out this repo, which contains demos which you can deploy into your AWS account, which use step functions with Lambda, Batch, and Fargate. Next is deep learning training. So similarly, we can just use SageMaker. And the advantage here is that it will have automatic handling of hyperparameter optimization and metrics, as well as data input and model output. And finally, it can also have hyperparameter optimization, as well as checkpoint handling. With Batch, you can have the same thing because you also run container in the cloud, but you will need to implement business logic, which I mentioned before, on your own, like hyperparameter optimization or saving the model. Finally, you can also use external GPU for training. In this case, it won't be fully scalable, but it will be the cheapest option. And your external GPU, which could be GPU on some other cloud provider or your GPU on premise, can download data and parameters from S3, train the model, upload it to S3, and report to step functions that it completed the training job. And then the model can be published into your production infrastructure on AWS. So feel free to check out same repo. It has also examples for deploying step functions with Batch and Fargate for training. And finally, inference. So when deploying inference, there is a more traditional approach where we can deploy something using clusters. The challenge here is that you will have to deploy a lot of different infrastructure services, like ECS for cluster, auto-scaling group to scale your cluster, a load balancer to route traffic to your instances, and spot fleet in case you want to utilize spot instances. Same architecture using AWS Lambda will be significantly simpler. So you can see here is just Route 53, API Gateway, and AWS Lambda. The challenge here is that you need to handle cold starts with AWS Lambda, as you have seen before when we compare different compute services. So what is cold start? Basically, when Lambda is invoked first time, there are certain steps which run on AWS side, like download the code, container setup, and some controlled by user side, like initialization and start of the code. In case with machine learning applications, it means that it's downloading image or zip file. It's about container setup, where we have Docker versus zip, as well as runtime. And on the user side, it means that we need to load libraries, download the model, and initialize it. So these steps which I mentioned are important to optimize if you want to have reduced cold start for your machine learning application. So you can see that you have multiple knobs here where you can store the model, which framework you can use, which configuration CPU RAM you are using, and which processor, Graviton Toro x86. Basically, you need to make sure to find the most suitable parameters based on your model. So usually lighter inference frameworks, TF-Lite, OpenVINA, they take less time to initialize. With processor, Graviton 2 can also be faster compared to x86. And for zip versus Docker image, you need to try different options and see what works best for you. So some life hacks to keep in mind. With storage, store a model in memory after load for warm invocations, so you don't load the model twice. You can store it in EFS instead of S3 for faster load. Also, you can store part of the model with your libraries for faster initialization. And if you download it from S3, you want to download it in parallel. Next is architecture. So you could separate your machine deep learning model into different layers and multiple lambdas and chain them. That's one option to reduce cold start. Another approach is to optimize RAM CPU to optimize your costs and check if Graviton 2 Lambda will work for your case faster and cheaper. So how do you know if Lambda is for you? So if you want to deploy it for like some small project or pet project, or you have a very simple model, or you have peak loads, it will work better for your case. But if you have to have real-time response and you need a lot of data and processing power, then cluster would be a more suitable approach. So to summarize, cloud workflow services are best for end-to-end deep learning pipelines. And depending on the context, you can use different AWS services for machine learning application. And if your context changes in the future, you can replace some services with other services. For example, you can start with SageMaker and then switch to AWS Batch. And finally, serverless pipelines can be easily deployed even for small machine learning projects. So you can deploy one pipeline for research application, and then it can evolve for using in production application. So thank you very much for your time. Here are the links to the repos which I shared throughout my presentation. They have examples for deploying different libraries to AWS Lambda or deploying step functions with Batch, Fargate, and SageMaker, as well as different benchmarks for EC2 instances and Lambda. And link with my website where you can also find same demos. Thank you very much and would be happy to connect.